Well, hello, class, and today we're going to be talking about the behaviors of light. And so we've talked a little bit about what transverse waves are in an overview, what a crest is, a trough, a resting point, wavelength, frequency, all that stuff we've already gone over in the intro to light waves. And so you want to make sure you keep those notes around. And then we're going to add to it by talking about the behavior of light and how it interacts with the world around it. And so, um, transverse waves travel in straight paths. Those straight paths are called rays. And so, just like the sun's rays getting to Earth, any kind of light travels in what we call a ray. And remember, those transverse waves travel up and down like this, but they could go in a straight path, a straight trajectory until they hit something. And once they hit something, they interact in one of three ways. They bounce off. We call that reflection. They pass through it, transmitted or transmission, or they're taken in or absorbed as heat. And so we're going to look at some of these interactions today and how we use those for our benefit. First one is when a light is transmitted or travels through a different media, we call that refraction. When light is refracted, it goes through a change of speed as it goes through that different medium, and it also changes the angle of its direction. And so you see here in this picture, the light comes in at one angle, and then when it hits the different medium, it changes the angle and changes the speed, and so it bends as it's going through that. Another illustration here we have of light going through glass. And so the light comes in at one angle, changes direction, goes out at that original angle again. And so that light bends as it goes through that plane of glass. Refraction is the reason that we see a straw in a glass, that the straw, if we're looking at it as it's under the water, it looks at a different angle or maybe a different size than above the water. And that's because of refraction. It's also the reason when you look at a fish tank, if you look down from below or down from above in the fish tank, the fish looks like it's in a different place or a different size than if you're looking in through the side of the fish tank. That angle changes as it goes through different mediums. It's also when we look through a prism and you see the different lights break up. And so that angle of the prism changes the different angles of the light, and you start to see that white light, which is made up of all the lights, breaks down into its different frequencies, and we see that as different colors. We use refraction in lenses like eyeglasses or binoculars or telescopes, magnifying lenses, through convex and concave lenses that refract or bend light. And so a convex lens is one that curves outward, and a concave lens, like a cave, curves inward. Convex lens. A convex lens curves outward, as I said, and it converges or brings together light. And so you see this light as it travels from the left-hand side, it goes through the lens, it then bends down to a focal point. Once the light hits that focal point, it continues to travel and passes through. Now, when that happens, the image actually flips upside down. And so we'll play with some lenses and you'll get to see that when you're looking from in front of the focal point, the image is right side up. Once you pass that focal point, the image flips upside down. And then you have concave lenses. There's the ones that bend inward. So think of a cave. It goes in and it diverges light. It spreads the light out. As it passes through the lens, it spreads that light out and it produces a larger image. And so if you think of your eyeball being on this side and seeing light come in, and it spreads that light out, making the image look larger than what it really is. And so you need to draw both of those. Make sure you get down a convex lens that converges light and a concave lens that diverges light. In your illustrations, draw how the light comes through as you're looking at it. And so you can see what kind of image it might produce. Maybe even helpful to draw in your image where the eyeball would be. On this one, the eyeball is on the right-hand side, and on the convex lens, it's also on the right-hand side. So let's talk about reflection. Reflection, like a mirror, it reflects or redirects light by bouncing light waves that travel in a straight line in different directions. And so, three different types of mirrors that we're going to look at: plane, concave, and convex. And so, you see them have the same names as the lenses, but they actually operate or interact oppositely than the lenses do. A plane mirror is just a regular mirror. This is the mirror that you probably have in your bathroom or your room that you use to get ready in the mornings. And so, other than the image being reversed, it produces the same image. It's not changed. It doesn't bend the light in any way. It just reflects it straight back to you. And so, if you hold a word up to a mirror, it's backwards. But other than that, it's unchanged. Then convex mirrors. Convex mirrors would be ones like you might see in stores in the ceiling or in the corners that help people be able to see the security, be able to see kind of around the corner. Produces this wider image because it diverges the light. When the light hits it, it spreads the light out as it reflects it back. And so you can see around corners and see things at a different angle. But it does produce a smaller image. And that image is upright. And so these also have, you see these on side view mirrors of cars, which is if you look at the bottom of a side view mirror, it'll say image appears farther than, or image is closer than it appears in the mirror. That's because it's producing that smaller image that makes it look further away than what it really is. But you want that wide angle so you can see cars coming up beside you. Here's an illustration of how a convex mirror works. And so as light comes in, it hits the mirror and it bounces out because of the curve of the mirror. When you draw this, you don't need to worry so much about the focal point for a convex mirror. You just need to be able to see that the light comes in and then bounces outward off the mirror, producing a wide angle. Then we have concave mirrors. Concave mirrors curve inward like a cave. And they converge light. When light hits it, it bounces inward because of the curve of the mirror. And if you're close up to it, it's going to produce a magnified image. And so you see the picture up here of the little girl that's up close to the mirror. She's much larger in the mirror than she is in reality. But if you're farther away, it produces an upside down image. And so you see the boy over here. This is like if you've ever looked in a spoon. If you hold it farther away, that image flips upside down. When we look at this illustration, you can see why. The light comes in and it hits the mirror, and because of the curve of the mirror, it pushes the light or reflects the light back down to this focus point. Then once the light hits the focus point and goes beyond it, the image that was here is now at the top, and the image that was at the top is now at the bottom. And so it flips that image upside down. Again, we'll play with these. You'll get to see that. You'll get to kind of manipulate some mirrors and some lenses to be able to identify which ones are which. Remember, concave curves inward, convex curves outward. And so you're going to need to draw both of these, showing how the light reacts on it. The focal point is not so important for us, just being able to see how that light interacts. Converge comes together, diverge means to spread apart. Another interaction with light that we need to look at is this idea of diffraction. Diffraction is when light bends around a corner or scatters and spreads out after going through a small opening. And so this would be like light coming in through a doorway into a dark room. It spreads out. Now you see in a small gap here that it spreads out more. This doesn't mean light is coming through more because the gap is small. It just means that it's curving more as it comes through. In a large gap, doesn't curve as much, but more light would probably be coming through because the gap is larger. And so this happens with all types of waves. And so we're going to watch a little video showing it with water waves, but you can see that the same way it reacts with light waves as well. And so pay attention to this video, and so you can see what how the light reacts when it comes to diffraction.
The next thing I want to look at is what happens to a water wave when it passes through an aperture. Well, I fitted an aperture here, but it's rather too wide for what I need at the moment. So if I fit these sliding doors, I can make an aperture that's about 3 centimeters across. And if you now look at the screen, you can see that as the waves pass through the aperture, they spread out. This spreading out of a wave as it passes through an aperture is known as diffraction, and it's a property of all types of waves. So what do you think controls how much the wave spreads out? Well, one possibility is the width of the aperture. And what do you think would happen if I made the aperture smaller? Well, you might be surprised to learn that a narrower aperture leads to more spreading out of the wave, more diffraction. If instead I make the aperture wider, then after it's settled down, you can see that the wave becomes less spread out. The diffraction is less pronounced. And if I were to make the aperture very wide indeed, then there'd be hardly any diffraction. Well, I'm now going to return the aperture to its original width and take a look at the effect of changing the wavelength of the wave. Now remember, I can change the wavelength by altering the frequency of the paddle using this control here. If I make the wavelength longer, you can see that the waves become more spread out beyond the aperture, more diffraction. And if I make the wavelength smaller again, here's where we started, then even shorter wavelength, then there's less diffraction. So here are the two separate factors that affect the diffraction of a wave passing through an aperture. The wave spreads out more if the aperture is made narrower or if the wavelength of the wave is increased. And conversely, it spreads out less with a wider aperture or a shorter wavelength. In fact, all kinds of waves, not just water waves, exhibit diffraction at an aperture, as long as the aperture is not too big.
All right, so you see the change in the space or the opening changes how much it diffracts as that wave comes through, and light works the exact same way. One other thing for us to look at is the idea, this idea of interference. And so when you have two openings in a wall, that wave's going to come out and diffract around, and it's going to cause interference with each other. And so remember, interference occurs when two waves collide. Where the crests meet, it magnifies the wave, and that's called constructive interference. And so if you think of constructive, building something, construction, the wave gets larger. And so you see these spaces here where the wave has become larger, and destructive or destruction, tearing down, in these blank spaces where the wave gets smaller because of the destructive interference. They cancel each other out where the crest and the trough meet. And so we've got one more video to watch. This is an interesting one that demonstrates how constructive and destructive interference works in light rays. And so I want you to, as you watch this original double slit experiment, I want you to see if you can predict what's going to happen as the video is going along. He asks people, and I'm kind of a man on the street kind of thing, asks people to make predictions. And so you make those predictions as well. And then once it's over, I want you to explain why it happened the way it did. And so be paying attention to see, can you explain why the light interacted the way that it did? And so we'll watch the double slit experiment.
What is light?
What is light? What is light? That's a good question, isn't it? What is light?
Isn't it an element?
Light is brightness, I guess. We have auras,
We all have auras.
which are light.
Yes, they are.
It lights up the room. It makes it not dark.
What's the difference between blue light and red light?
The colour.
It goes in your eyes and then you see stuff.
They range from white to red to orange to green. It's like the chakras of your body.
Can you see my aura?
No, not particularly right now.
Is it too bright out?
It's very sunny out here today.
Does that make it harder to see someone's aura?
Not necessarily.
If I was to explain it to a blind person, right?
Yeah.
It would be the difference. You see nothing whatsoever as a blind person, whereas I see things in front of me.
To be fair, the question of what light is not an easy one. For centuries, the greatest minds in science debated this issue. In the late 1600s, Newton proposed that light was a stream of particles, or corpuscles. He proposed this in his treatise Optics. But at the same time, a Dutch physicist named Huygens proposed that light was a wave. And this debate raged on until it was settled by the experiment I've recreated today, Thomas Young's double-slit experiment. To make sure I got the experiment right, I went to the original source. With the help of Brady Heron, I managed to get into the vault underneath the Royal Society in London. There I found Thomas Young's handwritten notes from 1803.
I brought into the sunbeam a slip of a card, about 1/30th of an inch,
in breadth,
and observed its shadow, either on the wall or on other cards held at different distances. Besides the fringes of colors on each side of the shadow itself was divided by similar parallel fringes.
smaller dimensions. Wow.
This is an experiment so simple that you could make it at home, and yet so fiddly that I have never seen it before done with sunlight.
I was thinking about doing it in a box, like a fridge box.
And you could take it out on the street.
Taking it out on the street.
Could I possibly interview you guys for about a minute? We're doing a science experiment. I have here is an empty box. And this is a little eyepiece where we can look in, and this is a hole. And I'm gonna place this slide above that hole. And if you look closely, you'll see that there's two openings. Very narrow openings side by side. It's a double slit. Now before we have a look, we need to tilt it towards the sun a little bit. So we want the sun to hit this double slit directly. What are we going to see on the bottom
Well,
of
the
the
obvious
box?
thing you think you're going to see is you're going to see two lines.
2 lines on the bottom of the box. 2 bright bands.
Two little lines. Yeah. I think it'll be one line instead of two.
I could expect to see the whole box lit up.
It'll probably be a kaleidoscope of some sort.
A bunch of colors.
Probably, yeah.
Rainbow, different colours.
There, have a look. You expected to see kind of one line. Is that what you see?
No.
I see dots.
How many?
It's one circle.
Well, there's one in the middle strongest, two either side.
The two on the outside are multicolored, and the one in the middle is just white.
And kind of a rainbow.
The rainbow of colour as well.
Quite a few colours and lots of little dots.
Like there are more dots appearing.
I think I can even see more dots spreading along. Yeah, that's amazing. Yeah, I can see tons of dots now. Not tons, but I can see dots spreading across that way.
Either side.
Yeah, definitely.
Isn't that amazing?
Yeah, that's incredible. And that's just nothing else apart from
Two slits.
two slits. I can't believe- That's incredible.
But all we're doing is we're putting a light through two very narrow slits side by side. So how does this make any sense?
There's some kind of principle involved there that the average person is not familiar with. That's the only explanation.
No, I'm really confused by it, but I'd like to find out why.
People were debating, is light a wave or is it made of particles?
So what causes that?
Well, if light were behaving as particles, you would expect them to go through each slit and just produce a bright spot underneath. So we would see two bright spots on the bottom of the box. But if light's behaving as waves, then the wave from one slit can interact with the waves from the other slit. I've got a demonstration here on a little pond where we can see this with water waves. I have two sources of ripples, which are basically like the two slits. When I create ripples with a single source, they travel out with circular wave fronts. Nothing particularly surprising there. But if I add a second source of ripples, then we start getting an interesting pattern. This pattern is created by the ripples from the two sources interacting with each other. Where they meet up peaks with peaks and troughs with troughs, the amplitude of the wave is increased. That's what we call constructive interference. But if the peak from one wave meets up with the trough from the other, then we get destructive interference and there's basically no wave there. And this is exactly what was happening with the light. When the light from one slit met up, peaks with peaks and troughs with troughs, they constructively interfered and produced a bright spot. But if the trough from the wave from one slit met up with the peak of the wave from the other slit, they would destructively interfere and you wouldn't see any light there. It's light cancelling itself out.
This is basically the same as like having 2 drops of water fall in a swimming pool.
That's right.
Get exactly the same
and then
pattern.
they go and overlap. As this ripple overlaps with those ripples, down the bottom, you get a series of, you get like a bright spot, and then a dark spot, and then a bright spot, then a dark spot, then a bright spot. Now there's a slight complication, which is that sunlight is composed of many different colors, and they have different wavelengths. So obviously they're going to meet up at slightly different points. And that's what caused the rainbowing effects as we go further from the central maximum. You saw the ones to the right were slightly colored.
Yeah,
that's
it's
because
burgundy.
the reds are going to meet up at different places than the blues.
And that's all that makes the colour differences, is different wavelengths.
Exactly.
That's amazing.
So the difference between
So,
red and blue,
that red bin over there and the green part are just, I'm seeing
It's
that
a
and it's
different-
just different
different length.
wavelengths. And that's how we bring in all these beautiful colours all around us.
Exactly.
That's amazing. I'm amazed. Oh, good on you. Thanks, Beck.
Hey, thank you.
I have been enlightened, literally.